Hello and welcome back. We ended off last video talking about acceleration, and we're going to pick up with this video addressing some of the misconceptions that I commonly see in regards to motion and acceleration. So the first misconception that I often see in students is this idea that they think an object cannot have a velocity if there are no forces on it, or if there are only balanced forces on it. So that is not true. That is a misconception. The reality of that is that an object can have a velocity with no forces or only balanced forces, but it will not accelerate. The reason for this is Newton's first law. Okay, that was one of the first things we learned way back in September. And it says that an object will maintain its velocity unless acted upon by an unbalanced force. So without any forces, or only balanced forces, an object will maintain its both speed and direction, since velocity is both speed and direction. So an example of this is, let's imagine that you were out in space, and you were floating around and you had a wrench. And what would happen if you just threw the wrench away from your body? Well, we know that while you're providing it some force, it would accelerate, so it would go from no velocity to some velocity. And once it leaves your hand, you can no longer exert a force on it. So if you can't exert a force on an object, you cannot influence its motion. So that wrench will continue to move at a certain velocity away from you, even though there are no forces. So no forces, you can still have motion. Balanced forces, you can also still have motion. So this would be akin to something like, let's say you were trying to move a dresser, right? And you had two people who were on opposite sides of the dresser. One was pushing and one was pulling. So we also know that if you're trying to slide something, there is friction. So the two people who are pushing and pulling and friction are going to oppose each other, and that can cause that object, once it starts moving, to move at a constant speed. So the push and pull and the friction are balancing each other out, but the object still has velocity. All right, the next misconception that I often see is as follows. If an object is moving forward, it must have a positive acceleration. Likewise, if an object is moving backward, it must have a negative acceleration. That is incorrect. The reality is that the direction of movement and the direction of the acceleration can be different. There is also this idea that a positive acceleration means speeding up and a negative acceleration means slowing down. And that is also incorrect. But let's explore that. So if you think back, remember what we did at the beginning of the forces unit when we were starting to talk about acceleration. We took the basketball and the meter stick. And what we did was we rolled the basketball in certain directions. If you remember, there was a line of tape that represented the number line at the back of the room. And so we pushed the ball in one direction, and then we pushed it with a meter stick, either forward, backward, towards the positive, towards the negative, etc. We kind of analyzed what those things caused, what type of motion. So the simplest possible case was when we rolled the ball toward the positive direction, and then we used the meter stick to push it in the positive direction. And we saw that quite clearly a positive velocity and a positive acceleration, positive acceleration means that it will speed up, right? So that's good. The next simplest case, or the next most intuitive case, I suppose, is when we had the ball roll in the positive direction and then we pushed it towards the negative. So a positive velocity with a negative acceleration, it slowed down. Okay, so that's intuitive. If you're moving forward, you get pushed backward, you're going to slow down. Now, when we move towards the negative side, things got a little more interesting. So the first thing we did was we rolled the ball in the negative direction, and then we pushed it towards the positive direction. And the result was kind of interesting, because when we say positive acceleration, we think speeding up. That's not necessarily true. The direction, the sign of the acceleration, only indicates which way the object is changing its motion. So with a negative velocity and a positive acceleration, we actually saw the object slow down, right? So you might think, oh, positive acceleration means speed up. Not in that case, right? And then the next one was we rolled the ball in the negative direction, and then we pushed it toward the negative direction. We caused a negative acceleration. So a negative velocity and a negative acceleration caused it to speed up. So what we kind of came out of this experiment with was the idea that when the velocity and the acceleration are the same sign, that means the object will speed up. If the velocity and acceleration are different signs, that means the object will slow down. All right, and the next misconception that I'm going to address here is that if an object is accelerating, then it must have a velocity. This is not actually true, and it is not true only in very narrow cases, and we'll talk about one of those right now. The reality of this is that an object can be accelerating but have no velocity, but only for an instant in time. All right. So this example we have done, and I'm going to describe it for you right now. Think about a ball thrown up into the air. What happens at the top of its flight? So when you throw a ball straight up, at the top, the highest point that it reaches, it stops for a moment, meaning it has no velocity, but it's still accelerating downward because it's changing direction at that instant in time. While we throw it up, gravity causes it to slow down. At the very peak, gravity causes it to change direction, and then when it goes down, gravity causes it to speed up. Right? So you can, for an instantaneous moment in time, have an acceleration but no velocity. All right, I want to do a quick problem here for you just to kind of refresh your memory on the types of problems that we might see. And this is actually going to be a combo problem. It's going to involve two different disciplines, but we'll see that it's no big deal. So we have an airplane accelerating from 100 meters per second to 250 meters per second in 2 minutes. If the airplane has a mass of 9,000 kilograms, how much force needs to be applied to achieve this acceleration? So let's start by doing what we always do, which is list all of our stuff that's provided, and then identify what we're being asked to find. So we accelerate from a VI of 100 meters per second to a VF of 250 meters per second in a time, delta t, of 2 minutes. The airplane has a mass of 9,000 kilograms. And what we're being asked is how much force. So we want to know what is the force that is required to generate this change in motion. So if we're looking at this, we know that it is accelerating. All right, we can tell because we have a change in velocity. We go from 100 meters per second to 250 meters per second. Now, if we're looking at formulas that we might consider useful, let's list things that we know. The most basic one is our F equals ma. We also know that v equals delta x over delta t. And we know that acceleration is delta v over, hold on. We know that acceleration is delta v over delta t, the change in velocity per unit time. So if we want force, the only thing that we know that we can see that has force is F equals ma. Okay, so if F equals ma, we have mass, we want force, but what we don't have is acceleration. We do have a formula for acceleration though. And let's do a quick sanity check to see whether or not we can solve this. All right, delta V is the same thing as saying VF minus VI. Do we have VF and VI? Yes, we do. We have delta T. So we could solve for this, which would then give us that. We know mass, and we can solve for force. So let's go ahead and do that. We will start with our lovely, we're going to use A equals delta V over delta T. Where that delta V is VF minus VI over delta T. So we're going to fill in what we know, 250 meters per second for VF minus 100 for VI over, now let's be careful. Notice what unit our time is in, 2 minutes. We want acceleration in meters per second squared. So we cannot use minutes. We will have to convert that into seconds, which of course is 120 seconds. So our acceleration ends up being 150 over 120, which of course is 1.25 meters per second squared. So we have found our acceleration. Hooray for us. Now we're going to go ahead and try to finish the problem. This is a case in which it is very important for you to identify what the problem is actually asking you to find, because you might get to this step, say, oh yay, acceleration, that's 1.25 meters per second squared, I'm done, when that's not really what the problem is asking you to find. The problem is asking us to find force, right? Force is our unknown. So we're going to go ahead and use F equals ma. Force equals our 9,000 kilograms times 1.25 meters per second squared, and we end up with 11,250 newtons of force. Have we answered the problem that we were originally asked to find? Yes, we have. So we are done. All right, so that's an example of how you would use kind of a two-step approach to solving a physics problem. It's not always just a very simple plug-and-chug type problem. Very often you will find that physics problems branch across multiple disciplines. So you will find problems that require knowledge of both kinematics and Newton's laws. It's very, very common. I suppose more common in the real world than in the physics textbook, but that's besides the point. All right, next. So since I just used that particular formula, I suppose it's important to actually get it down visually. Acceleration is a vector, and what its definition is, it is a change in velocity over a change in time. So it's a change in velocity per unit time. I just used the acceleration formula, but here it is again. A equals delta V over delta T, which is the same thing as saying VF minus VI over TF minus TI. And again, as previous, the TI, the initial time, is almost always going to be 0. So if you're told that it takes 2 minutes to accomplish a task, that is 2 minutes minus 0, right? That's where your time started at 0. So the units of acceleration are indeed in meters per second squared. So there's your formula. Let's move on. So one of the kinematics equations, the kinematics equations are a bank of equations that are all used to solve problems of motion. And they each require different types of information. And they each output different types of information, all related to motion. So this is the displacement under a constant acceleration formula. It reads delta x equals 1/2 in parentheses vi plus vf close parentheses times delta t. This is used to directly calculate the displacement of an object based on its initial and final velocity and how much time that took. So if you know the velocities and you know the time, you can use this formula to figure out how far the object went in that period of time. All right, so let's go ahead and use this displacement formula. A car accelerates uniformly from rest to a speed of 10 meters per second in 16 seconds. What is the displacement of the car in this time? So one of the most important pieces of information here is that it says it accelerates uniformly, right? That means that the acceleration is a constant rate throughout the entire motion. So let's pull out important pieces of information here. The one piece of information that's particularly important that you need to know is from rest. From rest means that your initial velocity is 0, right? At rest is, of course, an object that has no motion. So the next thing is a speed of 10 meters per second. So that means our VF is 10 meters per second in a time of 16 seconds. Therefore, our delta T is 16 seconds. And what we're being asked is, what is the displacement? Displacement, of course, is delta X. That's our unknown. So now we have our list of stuff and we've identified what we're being asked to find. So let's use this remaining white space over here to put together some equations. So you may know, we know, right, because I'm telling you that we're going to use the equation that we just saw to solve this problem, but that's not always the case, so it's good practice to write down multiple equations when you are asked to solve a problem, because in my opinion, seeing them all in a bank allows you to better suss out which one is the most appropriate, and it allows you to do the sanity check where you check off the information in the formula that is provided by the problem. So you can find out whether or not you have enough information to solve the formula. So let's go ahead and list some stuff. So we might as well list F equals ma. We don't know if it's going to be useful. So F equals ma is there. We are also going to go ahead and write down the definition of velocity, delta x over delta t. We know the definition of acceleration is delta v over delta t. And now we know that displacement is 1/2 vi plus vf times delta t. So we've got a list of formulas. Let's do our sanity check. Let's figure out whether or not we can solve these problems. So let's look first. F equals ma. Do we have F? No. Do we have mass? No. Do we know an acceleration? No. So this guy's out. Now, v equals delta x over delta t is only used in a constant velocity situation, right? So we know that one's out because we do not have a constant velocity. Now, acceleration equals delta v over delta t. We're not asked to find acceleration. We do know our two v's and we know a t, but we don't need acceleration, so that one's out. That's not necessary. Now, let's look at our actual, the formula that we are going to use, and let's see if we have everything we need. 1/2, that's just a number. Vi, we have. Vf, we have. Delta t, we have. Does it solve for what we want? Yes, it does. So we can move on. So let's use that formula. Delta x equals 1/2 vi plus vf delta t. So delta x equals 1/2 vi of 0 plus vf of 10 times delta t of 16. Gives us a delta x of 1/2. 0 plus 10 is 10 times 16. Delta x equals 1/2 of 10 is 5 times 16. Delta x equals 5 times 16 is 80 meters. Have we solved for what we were asked to solve in the problem? Yes, we have. All right. So that's the example using that particular formula. Next video, join me for the next kinematic equation. All right. So look forward to that. See you in the next video.